In front of you is something no human has ever approached. A black hole. A region of space so powerful that even light cannot escape it. In your hands is something much less dramatic. A simple soccer ball. Now imagine throwing that ball toward the black hole. What happens next? Does it disappear instantly? Does it explode? Or does something much stranger happen before it finally vanishes? And the most important question of all: how long could it actually survive? To answer that, we need to follow the ball on a journey toward one of the most extreme objects in the universe. A journey where gravity bends space, time begins to slow, and the laws of physics start behaving in ways that feel almost impossible. The soccer ball leaves your hand. There is no air in space. No wind. No sound. The ball simply drifts forward in complete silence. At first, nothing about its motion seems unusual. It rotates slowly, just as it would if you threw it on Earth. But far ahead of it, something invisible is waiting. The gravity of the black hole. Even from a great distance, the black hole is already pulling on the ball. At first the pull is gentle. Almost unnoticeable. But with every passing second, the force grows stronger. The ball begins to accelerate. Faster. And faster. And faster. The closer it moves toward the black hole, the more dramatic the journey becomes. Because near a black hole, gravity does not behave the way we experience it on Earth. Something far stranger begins to happen. Gravity begins bending space itself. Most people imagine gravity as a force pulling objects downward. But according to Einstein's theory of relativity, gravity is actually something different. Mass bends the fabric of space and time. And objects move along the curves that mass creates. A black hole is the most extreme example of this idea. Its mass is so incredibly dense that space itself is warped almost beyond recognition. If you could see space around the black hole, it would look like a deep funnel stretching downward into darkness. The soccer ball is no longer simply moving forward. It is sliding down this invisible curve in space. From far away, an observer might see the ball begin to spiral inward. Slowly at first. Then more rapidly as gravity strengthens. But the soccer ball itself would feel nothing unusual. It is simply falling. And as it falls deeper into the warped space around the black hole, another strange effect begins to appear. Time itself starts to change. Near extremely strong gravity, time does not flow the same way it does on Earth. The stronger the gravity, the slower time moves. This phenomenon is called gravitational time dilation. Mathematically, physicists describe the slowing of time near massive objects with a relation like this. This expression shows how time experienced near a massive object differs from time far away. As the soccer ball moves closer to the black hole, time for the ball begins to slow down compared to the rest of the universe. To someone watching from far away, the ball would appear to move slower and slower. Its motion toward the black hole would gradually seem to freeze. Light coming from the ball would also stretch into longer wavelengths, turning redder and dimmer. Eventually the ball would appear almost completely motionless right at the edge of the black hole. But from the ball's own perspective, nothing unusual is happening. Time feels normal. The ball continues falling. Closer. Closer. Toward the invisible boundary known as the event horizon. The event horizon is the point where escape becomes impossible. Once anything crosses this boundary, it can never come back. Not even light. From the outside, the event horizon appears like the surface of a perfectly dark sphere. But it is not a physical barrier. There is no wall. No solid surface. If the soccer ball were falling toward a supermassive black hole, it could cross the event horizon without even noticing. There would be no sudden jolt. No explosion. No flash of light. The ball would simply continue falling into the darkness beyond. But deeper inside the black hole, the real danger begins. Because gravity is no longer pulling evenly on the entire object. And that difference in gravity leads to one of the strangest processes in astrophysics. Imagine grabbing the soccer ball with both hands. Now imagine pulling each side in opposite directions. Eventually the ball would stretch. Then tear. Near a black hole, gravity performs the same action. But instead of hands pulling the ball apart, it is gravity itself doing the stretching. The side of the soccer ball closer to the black hole experiences stronger gravity than the side farther away. At first the difference is small. But as the ball falls deeper into the black hole's gravitational field, the difference grows dramatically. The front of the ball begins accelerating faster than the back. Slowly the perfectly round shape begins to distort. The sphere becomes slightly oval. Then longer. Then thinner. Physicists call this process spaghettification. Because objects are stretched into long, thin strands, like spaghetti. For a soccer ball, this stretching quickly becomes destructive. The rubber panels that form its surface are not designed to withstand such forces. The stitching begins to strain. The seams start pulling apart. And eventually, the structure of the ball can no longer hold. The first thing to fail would likely be the stitching. The threads holding the panels together snap under the immense gravitational difference. The ball begins to tear open. Air trapped inside escapes into the vacuum of space. Rubber panels peel away from each other. What was once a simple soccer ball is now a collection of fragments. But the destruction does not stop there. Each fragment experiences gravity differently depending on its exact position. Some pieces fall faster. Others lag slightly behind. The debris stretches into a long stream falling toward the center of the black hole. Eventually the fragments become so spread out that the original object is no longer recognizable. The soccer ball has been completely destroyed. But the pieces are still falling. Still accelerating. Still moving toward something even more mysterious. The very center of the black hole. The singularity. At the center of every black hole lies something physics still struggles to understand. The singularity. It is thought to be a point where gravity becomes infinitely strong and density becomes infinitely large. In this region, the known laws of physics begin to break down. Our current theories, general relativity and quantum mechanics, cannot fully describe what happens there. As the fragments of the soccer ball approach the singularity, their fate becomes uncertain. They may be crushed into an unimaginably dense state. They may lose all recognizable structure. Or the information describing their existence may somehow be preserved in ways scientists still debate today. The truth is, no one knows exactly what happens inside a singularity. It remains one of the greatest unsolved mysteries in modern physics. But one thing is clear. Once the soccer ball crosses the event horizon, its story becomes hidden from the rest of the universe forever. Now we can finally answer the question. How long could a soccer ball survive inside a black hole? The answer depends on one critical factor. The size of the black hole. Small black holes, formed from collapsing stars, have extremely strong tidal forces near their event horizons. In those environments, the soccer ball would likely be stretched and destroyed within just a few seconds. But supermassive black holes are very different. These enormous objects sit at the centers of galaxies and contain millions or even billions of times the mass of our Sun. Because they are so large, the gravitational difference across small objects near their event horizon is much weaker. In that case, the soccer ball might remain intact for minutes before tidal forces finally tear it apart. Eventually though, gravity always wins. Every fragment of the ball would continue falling inward. Deeper. And deeper. Toward the singularity. The soccer ball disappears forever. Not burned. Not exploded. But slowly erased by the most powerful force in the universe. Gravity. And once something crosses the event horizon, the universe outside may never know what truly happens to it. The ball is gone.